All right, so welcome. Good afternoon. I said good morning earlier, but that was wrong. It's afternoon. So here I get to fix it. So today I want to think about, I'm just trying to remember if there was something I needed to say to you guys. I haven't set a due date for the chapter 1 code. I'm tempted to just kind of leave it open and for you to work on and have a due date much later on after reading break probably, or kind of during reading break, maybe at the end or something like that. And because that way you can kind of work through it at a reasonable pace and you can kind of work together and chat together, and I think that'll be good. Remember, the only reason I'm making you do this is so that you can feel like you have a really good handle on what's in the textbook, right? And so it's really just, it's for you. It's not for me to see that you can copy and paste code. It's for you to really get down and get nitty gritty with figuring out how these things work. And that's going to be a lot of your job in the future, right? Is just kind of taking some code or kind of understanding how something works and then applying it to a new situation, right? And so that's going to be part of your job. So it's not for me to see that you can replicate code. I don't care about that. It's for you to have a library of code that you can use for future projects. Okay? So that's why I'm a little bit easygoing on the due dates. And I don't know how it slipped my mind, although yeah, I do. Whenever anything isn't hard copy, paper copy, I forget to mark it. And that's my bad. But so I haven't marked your labs recently. So I'm gonna do that this weekend. I've got a big weekend planned of marking. So don't worry, I'll get caught up. I'll try to stay on top of things. No promises though. I'm really good at forgetting. So let's see here. So we're going to get into chapter 2, which starts off with just kind of a lot of theory that we've already seen most of it before, but not in a data science context. Okay, and so chapter 2 is on data and sampling distributions. So how you read that is very important. Data and sampling distributions. One distinction that we're going to make is that this is the same as saying data distributions and sampling distributions. And a lot of our focus will be on the comparison of the two. Okay, so we're going to have data distributions, which we're familiar with, right? That's when we make a histogram of just one variable, so of some data. And then we're going to move into the sampling distribution, which is also going to be a histogram typically, but a sampling distribution is the distribution of a statistic. So a sample statistic, for example, the mean, okay? And I know we talked about the central limit theorem in Stat 230, and so that's going to come back into play, and that is for the sampling distribution. But we're going to have some other methods to rely on rather than just the central limit theorem, which applies mostly just to the mean. But the mean is the most common measurement that we're interested in, right? So it's good to know something about the mean. Okay, but before we can talk about the distribution, we need to revisit just sampling in general, right? And so sampling data, the most important part of sampling data is to make sure that our sample is representative of the population. I've said it once, I'll say it again, right? And so that's going to be a recurring theme, both in statistics, a lot in statistics, but also in data science, right? And so let me just jot that down. So to collect data, we rely on sampling, so random sampling. To collect data, we rely on sampling, typically from a population. So I'll say from a population, but in brackets, from a population. Okay. So to collect data, we rely on sampling, right? And one thing that we need is, in order for our sample to be representative of our population, so, and in order for our sample to be representative of the population, we need to use some version of random sampling, right? So we need to collect our sample or collect our data randomly. And we've talked about some methods, right? Simple random sampling, stratified random sampling, we talked about in Stat 230. Those might just ring a bell. You might not remember what they are. You can easily look them up, right? And so that's not the hard part. It's just remembering that we need to have a sample that's representative of the population. And so the only way to do that is to collect a random sample. Most kind of beginners want to collect a sample and force it to look like the population. Oh, I know the population looks like this, so I'm going to force that to happen. And that's useful sometimes, but most of the time it's better to have just a random sample, a completely random sample, and that will end up being representative of the population. So to finish this thought, to collect data, we rely on sampling. And in order for a sample to be representative of the population, we need to use random sampling. We need to use random sampling. What does it mean to collect a random sample? And so think about that. But also, why do we care about samples? Especially if we have, coming from a classical statistical background, right? Remember, there were no computers. And so then collecting data was very difficult, right? And very expensive. And also we couldn't use a computer to calculate the standard deviation. So if we had a huge sample, it was hard to work with that sample, right? They still did it, but it made it hard to work with, right? And so we want to collect a sample that's representative of the population. But now I'm guilty of this, right? Why do we care? Let's just use, even if we're dealing with big data, right? Which big data is kind of this vague idea of it's not data that's special in any way. It's just when you have tons and tons and tons of data points, right? So it could be as large as 1,000,000 by 1,000,000, right? So imagine a spreadsheet that's 1,000,000 by 1,000,000. So we have 1,000,000 observations, which is very easy to come by now, right? So it would probably be more like 30 million and we could collect 1,000,000 variables if we wanted to, right? Even in the 100,000s of variables, this data set would get huge. The idea stays the same though for big data. We just come across a couple of different problems later on, but for now the ideas are the same for big data as for let's call them normal data, although normal means the normal distribution, so that's why I'm putting air quotes around it. But right, our usual data that we talk about, kind of normal sized data sets, I guess, versus big data, the ideas are very similar. Okay, it's just we're dealing with huge amounts of data. Now, what we're going to find is that even if we have big data available, right, we're often just going to sample from that data, right? And that gives us enough information. So we're still going to be sampling. It's just whether we're sampling from a population or from a big data set. Okay? But either way, our sample has to be representative of the population. Okay? Otherwise, we can't learn anything from the sample. Right? And what we're going to find is we're going to build on the sample. So if you're building on a sample that doesn't represent the population, that's bad, right? And so that's why we need to start with a good sample. What does it mean to have random sampling? Oh, sorry, let me just check. It says my internet connection is unstable. Let me know if you're having troubles. I'm on the good one, so I don't know what to do here, but it is claiming it's unstable. So, okay, nice. Thank you. So I think we're good. Let me know. Although it might not deliver your messages to me if I have an unstable connection. So anyways, let's just keep going. So what does it mean to conduct a random sampling, or what does a random sample actually mean, right? So random sampling by definition is when each individual or data point or observation or whatever has the same probability of being selected into the sample, right? Which means that on the flip side, right, if there's bias, then it means that there is a higher probability of selecting some of the observations over another, right? And so random sampling is when each individual I'm going to say individual, but it goes for, you know, kind of businesses, or I'm just going to call them individuals. So when each thing that we're sampling, which is the individual in the population, has the same probability of being selected into the sample. Okay. And so the opposite of that, right, if we kind of remind ourselves what bias is when we're systematically selecting individuals to be in our sample, which would mean what? It would mean that each individual in the population does not have the same probability of being selected into the sample, right? Because some individuals would have a higher probability of being selected. Okay? So versus bias, or biased sampling, maybe I'll say, which we usually define bias as systematically favoring certain individuals. Okay. Oh yeah, so if random sampling is done, then usually you're going to end up with a normal distribution, but what's going to happen is it's going to reflect the shape of the population, right? So if the population is skewed, then your sample is likely going to also look skewed. But what we're going to get to is what's cool is even if you're pulling from a skewed distribution, then as long as your sample size is large enough, then the mean, the distribution of the mean, which brings us to sampling distribution. So I am jumping ahead a little bit, but it was a good question and to kind of get us going here. The distribution of the mean, even if it comes from a skewed distribution, if I look at the distribution of means, that's going to follow a normal distribution, right? And so that's kind of the cornerstone of traditional statistics, and we're going to keep using that, but in a slightly different way. Okay, so biased sampling, jumping back, but good, we're going to get there, is systematically favoring certain individuals, which means that and I guess I could just steal it, but each individual in the population does not have the same probability of being selected into the sample. Okay. So here I'm just going to highlight the does not because that's the only difference. Okay. And so let's see here. So that's going to be bias sampling. Now, there are times when the bias is unavoidable, right? So if we think about restaurant reviews, for example, or any review, but let's just focus on restaurant reviews just to kind of have a focused example. Okay, so then the bias is unavoidable, right? You're only going to get reviews from people who had an extreme experience, right? Extremely good or extremely bad, or people who are being paid to write the review, or people who are just more inclined to write reviews, right? I have good intentions and I have a list of reviews that I plan to write at some point, but I just never get around to it. So I would consider myself a person who really doesn't write reviews. I want to, but that doesn't show up on a Google review. Oh, Emily really wants to write a review, but hasn't yet, right? And so those don't count. And so when we look at those reviews, then we've got this biased sample, right? So it's not representative of the entire population, okay? But it's okay because, so although it's not representative of how the entire population feels, they are comparable, right? We can still use them to compare to restaurants, right? Because they're facing the same bias in either situation, right? They've still got, people who are more inclined to write reviews, extreme experiences, right? Extremely bad, extremely good, just kind of things that prompt you to write a review, right? Both restaurants are dealing with that, which makes those reviews comparable, right? But if we were trying to talk about the entire population, how the entire population feels about one restaurant, those reviews are not representative, right? And so, so consider the bias in restaurant reviews. Right? People who write reviews, people who write those reviews or give those ratings, right, typically have had extreme have extreme experiences, good or bad, right? In either direction, it doesn't actually matter, right? Extreme experiences have been paid to write the review, have been paid, or just are generally more likely to write reviews, right? Generally more likely to write reviews, right? And those people might just be completely different in many aspects, maybe in taste of restaurants, right? Those people might be completely different from people who don't write reviews, right? So here, these people might be different from people who don't write reviews. People who don't write reviews. Thinking about socioeconomic status, right? That's going to be a huge player in restaurant reviews. How do people feel about this restaurant, right? If you think that a $50 meal is cheap, then that's going to be different from someone who thinks a $50 meal is very expensive. I think it's very expensive, right? And I don't write reviews, so you can see how that would kind of play out, right? So you'd have this potential division in people who write the reviews and who don't. So what we're dealing with here is bias, right? So all of these are introducing bias. Okay. That we can still work around bias, right? As long as we know the limitations. So we can still work around bias, keeping in mind the limitations. Keeping in mind the limitations. Right? We can compare restaurants because they're both facing the same bias. We can compare restaurants because they face the same, and I'll put same in quotes here, the same bias, right? But we cannot use reviews as a reflection of the general population, right? We cannot, and maybe I'll phrase this in a way that matches our previous terminology, right? We cannot use the reviews as being representative, or we cannot assume the reviews are representative of the general population. Okay. So just kind of interesting to think about, you know, if there is bias and all we're doing as we're collecting data is trying to eliminate bias, but sometimes there's just no way around it. The data that we have will be biased. So then we need to remember, okay, then my limitations are these, right? I can compare these two because they're facing the same bias, but I can't draw conclusions about how the general population feels, right? And so we need to kind of state those limitations. Okay. So let me just make sure I've talked about all the things I wanted to talk about so far, which in turn. Okay, so Let's see here. So I would say that with big data, and so even with big data, or I would almost say especially with big data, the data quality that we have is way more important than the data quantity at this point. So it used to be, you know, going back, let's say 100 years, and you've collected a sample, it used to be, you know, just collect as big a sample as you possibly can, because we're so limited in how much information we can collect, right? And so, you know, if you're sampling, I love manatees. So if you're sampling manatees 100 years ago, then I'm just thinking what that would look like. But anyways, then the goal would just be look at as many manatees as you possibly can, because we're limited by how much we can do. But now with big data, I mean, Google has every day the search results, and the textbook talks about how each word in the English language is broken up and is a variable, right? How many searches contain the word the, right? And how many searches and how many searches contain the word statistics, right? And so, and that kind of thing. And it would be a binary variable, right? 0, 1, 0, 1. And each search would have many, many, many zeros, because our search phrases are only so long, right? And it would just kind of 1, 1, 1, the words that you use. And then we can analyze that. So we have lots and lots of zeros. And so we need to kind of pare down this huge data set to something that we can work with more easily. We could work with the entire data set, but we are still kind of limited by computation, because sometimes it would take days for these computations to run, depending on what you're asking it to do. Usually for model building, right, you would need lots and lots of horsepower to get through those. So then we rely on sampling, and the benefit is our sampling results are typically just as good as if we use the entire yeah, so we exactly, thank you. Yeah, so we have, well said. So we have the opposite situation now, but we kind of go the other way. We say, okay, now let's pare it down, and we come back in the middle, right, with this sample. Usually it's a little bit bigger than what we would have had, but exactly, awesome. Okay, so I would say that even, and I'm gonna say, I'm gonna go as far as saying / especially with big data, data quality is going to be more important than quantity. So even / especially with big data, and I put big data in quotes because it's kind of this construct that we have. Data quality is often more important than quantity. So random sampling, even from a big data set, right, is going to improve the quality and reduce bias. So random sampling can reduce bias, just to write it out how I have it in my notes here, can reduce bias and improve quality. So that's kind of where we're going, and I'll just make a note of the different sampling techniques that we can use, right? Some common ones are a simple random sample, where you would just assign a value to each individual in your population, and then randomly select numbers, and you're in, you're out, you're in, you're out, and then go that way. Or we can do something more sophisticated, like stratified random sampling, or multi-stage sampling. There's lots of different ways that we can do it, but random sampling, the reason we do it, random sampling can reduce bias and improve our quality, right? So some random sampling techniques, and maybe I'll call them methods. Some random sampling methods include simple random sampling, stratified random sampling, how does it improve the quality? So the quality of the data is referring to how representative it is of the population. So the quality here is really referring to how representative it is of the population. Awesome. So some of these random sampling methods, and then it goes on, there's multi-stage sampling. Oops. Multi-stage sampling. And the list goes on and on and on. But those are the most common ones. And let me just grab the textbook here, because they have some really good, and it's funny because some of these further reading sections that they have, I've read a lot of them, so that's kind of fun. Not, entirely, but I'm aware of a lot of them, so that's kind of fun. And it's just a good, I mean, some of the articles that they're referencing are a little bit out there, right? I wouldn't have come across that in a million years, but like one is from, what was it from? It was some non-statistical journal, but anyways, the further reading sections are really good. And if you have time to kind of dive in, or if you're more curious on a topic, then that might be good. Oh yeah, so after what section? The further reading from random selection has, it mentions, and I only have this textbook right now. So a useful review of sampling procedures can be found in Ronald Fricker's chapter, Sampling Methods for Online Surveys. So they've got kind of a couple of things if you're interested in other sampling techniques. Okay. And so here, see further reading for which section? I think it was random sampling, right? What did I say? Yeah, random selection. For random selection, if interested. I'm not saying that as a clue or anything. I'm not going to go find it. I have a pretty good idea of what's there. But if you're interested, then that's where I would send you. Okay. So one kind of fun idea. So I am skipping a couple of sections but I am assuming that you've read the textbook, right? And so, or at least, half of chapter 2 so far. That's what we're doing today. And then for next day, we'll do the remainder of chapter 2, right? So I am assuming that you're reading the textbook at this point, right? That's why I picked a free textbook. And so, so I am skipping a couple of things that we're not going to build on necessarily, but that are nice to know. One thing that I do want to point out is this idea of regressing to the mean. So regression to the mean is this kind of cool thing that happens. So if you observe an extreme observation, right, then the following outcome is going to be less extreme. In fact, it's going to be closer to the mean, right, than the previous outcome. And that's just how it is, right? And so that's regression to the mean. And it's this kind of interesting idea. So this is different from linear regression, although we can draw lines and then we're regressing to the mean, which is also on the line, right? But different from linear regression. So regression to the mean is this interesting idea of, and the most famous example is if you have two parents that are very, very tall, right, then you are going to be tall, but not as tall as your parents. And that's just a phenomenon, right? And if you have two parents that are very, very short, right, you're going to be short, but you're not going to be as short as your parents, right? So we all tend to the center. We all tend to the mean, right? And that's regression to the mean. So extreme observations, and I say both parents in that example, but I think it was established for the father, right? But of course, if you have two parents that are extremely tall or extremely short, then their child is going to be kind of moving towards the mean. So extreme observations tend to be followed by more central ones, right? And so the famous example and I'm paraphrasing, of course, is two parents that are extremely tall, will have tall children, but not as tall as themselves, okay, typically. So parents that are extremely tall, and so I say typically, and what does that translate to? Well, extreme observation, so two tall parents tend, which means it not always the case, but tend to be followed by more central ones, right? So parents that are extremely tall tend to have children that are tall, but not as tall as themselves, right? So tend to have children that are tall, but not as tall as themselves. That's just an interesting, just kind of natural phenomenon, and it's called regression to the mean, right? So it's this idea that, okay, an extreme observation is usually followed by a more central observation. So one thing that we keep in mind is that the reason we're collecting data is to measure something, right? We're either measuring something or we're modeling some behavior. Okay, so those are two different things. but they kind of go hand in hand. Okay, so we collect data. We collect data to measure something. For example, the mean. Okay. Or to model something. Right, so to model some outcome, whether that's numerical or categorical, right? We're going to get there. We haven't really built models besides a simple linear regression so far, but we're going to build models and we're going to try to model those outcomes. Okay, so we collect data to learn about the population, right? So we're trying to measure it or model it. Right, if this changes, I would expect to see a change in this much. Right? And so the problem is when we collect data, right, we use samples, but we also know that if I collected a brand new sample, it would be slightly different, right? Even if I have randomly selected and I have this great representative sample, it's a good sample. Even if I let all those observations go and I randomly selected and collected just as good of a sample, there's going to be variability there, right? And so that's what we're trying to harness, and that's what we're trying to learn about, right? How much is that variability, and how does that affect my measurement, for example, right? How does that affect my sample mean? How much wiggle room do I expect to have, right? And so put it on a fresh page here. We use samples to estimate, right, some measurement or a model. So we use samples to estimate a measurement or model. Okay. But even if we've collected a perfectly random sample, a perfectly representative sample, okay, but even if we have collected a perfectly, and I'll kind of say perfectly, so that means random, collected a perfectly representative sample, we understand that if we collected a sample again, if we collected a new sample, a new perfectly random sample, right, or perfectly representative sample, it would be different, right? It would be slightly different. But even if we have collected a perfectly representative sample, we understand that if we collected another representative sample, the measurements and the models would be slightly different. The measurements and models or models would be different. Right? So what we're facing here is this sampling variability, right? And so I'm going to highlight that here and say there will be sampling variability. There will be sampling variability. So how do I capture that sampling variability? You might remember the standard error of some measurement, and that's exactly where we're headed. So one thing to keep in mind before we do that is the difference between a data distribution versus a sampling distribution. Okay, and so a data distribution is the distribution of the data, so one variable, right? And so that's going to be individual values, the distribution of individual values. Versus a sampling distribution is the distribution of sample statistics. So for example, if I do go through and in theory, I collect a random sample and I record the mean, and then I let those guys go, and then I collect a new random sample and I record the mean. Now I have a sample, I'm collecting a sample of sample statistics. Okay, and that the distribution of those values will be the sampling distribution. So the sampling distribution is the distribution, the distribution of sample statistics over many samples, right? So we use this repeated sampling technique, and so far we've only seen it in theory. We say, okay, the mean follows a normal distribution with a mean of mu and a standard deviation of sigma over root n, right? And so we know that, and that's just because it's been established, and that is the central limit theorem, right? And so we are familiar with the central limit theorem. With the central limit theorem, which says that x bar, the mean of some observation or some sample, is going to follow a normal distribution with a mean mu and a standard deviation of sigma over root n. Right? This we call our standard error, sigma over root n, instead of calling it the standard deviation of x bar, which is the mean of x, right? Which incorporates sigma, which is the standard deviation of an individual value of x, right? Kind of tricky, right? So then instead of calling it the standard deviation of x bar, we call it the standard error instead. So the central limit theorem, and I'm going to just shorthand that because I don't want to write it out again. We usually denote it as the CLT, central limit theorem, right? So the central limit theorem says that it doesn't matter, and this is what we were talking about before, right? If you're pulling from a skewed distribution, then the data distribution might be skewed, and that's okay, right? We can still consider the mean, we can still consider the distribution of the means, and they will follow a normal distribution. Okay. So here, even if the distribution of X is not normal, right? If we consider a large enough number of means, right, then the distribution of those means will tend to a normal distribution. So that's the cool part about the central limit theorem. And so even if the distribution of X is not normal, which means the population is not normal, the distribution of the mean of X will be normal. The distribution, of X bar will be normal by the CLT. And that's just this crazy thing that we've developed. And if we think about, again, 100 years ago, if the mean is the thing that we're always interested in, then we were motivated to figure out the distribution of the mean. And it's this big finding, okay, well, it's always going to follow a normal distribution. And from there, we were able to develop things like the t distribution, right, to be able to approximate the distribution, right? And we were able to figure out Z scores and stuff like that, right? And so we were able to do a lot of things relying on the central limit theorem, but it's focused on the mean. What if I'm interested in something other than the mean? Then I don't have this anymore. I don't have the sampling distribution for many of the things that we could consider. Okay, but now with computers and kind of inexpensive computing, we're able to get around this. We're able to develop the sampling distribution every time, right? And we're able to kind of recreate it. So I want to talk about how that works, because that's going to be important, because we're not always just going to talk about the mean, right? And we're not always going to talk about the distribution, the sampling distribution of a sample statistic that we already know how it's distributed. A lot of our go-tos have been established and we know the sampling distribution already, but this is for when we don't. And even when we do, we tend to kind of steer away from this classical way of dealing with it. So let's see here. So even if the distribution of X is not normal, the distribution of X bar will be normal by the central limit theorem, right? And this sigma over root n is a measure, so that is the standard error, and it's a measure of the variability in X bar. So this is the variability in X bar. Okay. I can use this, I can leverage that. If the variability, if I want to minimize the variability, which I do, right, because I want my estimates to be close to the real X bar, right, or the real mean, sorry, mu, then how can I do that? I probably can't affect sigma, right? But I can affect my sample size. So by increasing my sample size, I can decrease the variability, right? Because if we take the root of n, then divide that into my sigma, then as I increase the root of n, which the only way to do that is by increasing n, right? But it's going to happen at a root of the time, right? And so that's how I'm going to decrease this overall value, right? So we need to know, okay, increasing my sample size is going to decrease the variability in X bar, right? And so that's good. So large sample sizes are still good in that way. Okay, so and I'm just going to kind of encapsulate it as, with modern technology, right? With modern technology, we can estimate, and that kind of gets weird. We can, I'm gonna have to use the word estimate, even though that's just me being hung up on a word, but estimate means something specific, right? It means to estimate the mean, estimate the model, right? It means taking sample information and applying it to estimate the population. But now I'm going to estimate the sampling distribution, and that's okay. With modern technology, we can estimate the sampling distribution of any sample statistic using the Bootstrap. And you might have heard about the Bootstrap before and potentially even used it, right? But I'm going to go through and assume that you haven't. So if you have, then that's great. It is very common that we use it. And so, so you've probably seen it before, but let's assume that we haven't, right? Especially because we didn't see it in Stat 230. We didn't talk about it. We didn't say we knew what it was. So the sampling distribution of any sample statistic using the Bootstrap. Okay. Jotted down what it is. So it used to be that we were limited to a small sample size. Okay, so that's how the Bootstrap was developed. But now what we're finding is using the Bootstrap actually gives us a really good idea of the sampling distribution. So, and that's a good thing. That's what we want. Okay, and so that's why we use the Bootstrap. So again, right, we're going to have the opposite situation with the same solution, stealing from the chat there. So right, and so we kind of have this method that we had to develop because we didn't have enough data, and then now, right, we're saying, okay, well, it still works, so we're just going to use it, but in a different way. Okay, and so what does the Bootstrap do? Imagine you have collected a sample. So now you're limited to this one sample, right? Which would have been the case before, right? When we were, let's call it poor, when we were data poor, right? Way back when we were data poor and we only had a small sample, right? And so what we would do is we would take random samples with replacement from that sample, right? And so I would basically replicate that sample many, many times over, okay? And it obviously didn't take off right away. People are kind of like, you can't do that, right? It assumes that you have a representative sample, right? But now we're able to do that, and we're able to focus on a good representative sample from our big data, and we're able to recreate samples that look slightly different, but based off of the same sample. So it does rely on having a good representative sample still, right? And so the Bootstrap, and maybe I'll start it on a new page here. Is when we have a sample. And so I'll start off and say that it relies on having a good representative sample to start with. So it relies on having a good, which is a representative sample. So I'll put good in air quotes, and then a representative sample. Right, so the Bootstrap does rely on that, and even if we don't, there's some wiggle room there because we are going to replicate things a lot of the time, and so we're going to have kind of a good sample of samples, if that makes sense. So it relies on having a good representative sample. And it allows us to estimate the sampling distribution of a sample statistic and allows us to estimate the sampling distribution of any sample statistic. Okay, so what we have is we have one good sample to start off with. Okay? And then, so the steps to the Bootstrap are, first, we're going to draw a sample, a sample value, okay, jot it down, and then put it back into the sample. Okay, so we're going to have two samples that we work with. We have our original sample, and then we're going to pull it and create a new sample. Okay, so draw a sample. And maybe what I'll do is draw a value from the original sample. And record as part of your new sample. And record it to create a new sample. Replace that value that you just drew back into the original sample. And so what I'm going to do is I'm going to shorthand these because this is getting insane here. The original sample, let's write it as OS, and then the new sample can be NS. Okay. So draw a value from the original sample and then record it to create a new sample. Okay. Replace the value into the original sample. And then you're going to repeat that n times, right? And that's going to be your sample size for each sample. Repeat n times. And n is still the sample size. Okay. And so I'm going to follow that up with repeat n times to create a sample of size n. Whoops. A sample of size n. Okay. So you've done that. You have your original sample, and then you pull one value out, you record it, and you do that n times, you put it back in, you do that n times to get a sample of size n. Okay. Every time that you're drawing from the original sample, you're selecting from the same values always, right? But you're randomly selecting from within that sample, right? And so that's how you're able to create this new sample, because the same value could be selected again, right? Because remembering the definition of a random sample is each value has the same probability of being selected. It doesn't matter if it's already been in your sample, right? So now we have a sample of size n, and now what we're going to do is we're going to do that again, right? But before we do that, or doesn't really matter. We collect many samples like this, and then we record the mean or whatever sample statistic we're interested in, right? If we're trying to replicate the central limit theorem, we would write down the mean, right? And so then step 3, let's say, is record the sample statistic of interest. For example, the mean. Okay, so you're going to record the mean, for example, or maybe you're trying to find the distribution of the median. That's fine, right? We can do that. We could have collect a sample of medians, right? And so if you record the mean, then you have one mean. Now we're trying to collect a sample of means, right? To figure out what the distribution of the means is. And so then you're going to repeat this, repeat 1 through 3, steps 1 through 3, and we're going to use a capital R to denote how many repetitions we have. Don't be confused by the software R and or the language R and this R. They are different, but the reason we're going to use it is because the R code uses R, and it's just the number of repetitions, right? And so repeat 1 through 3 R times, right? And I am pretty sure R is the repetitions, I think. I'm willing to write it down and stand by it, but I didn't look into it. I just assumed that that's what it is, right? And that makes sense to me. So you're going to repeat it R times, okay? And then, so now this is going to mean that you have collected a sample. So now we've established a sample of R means, right? Or R sample statistics. This this results in a sample of R sample statistics. Right. For example, a sample of R means, right? If we're trying to match the central limit theorem. So now that I have a sample of sample statistics, now I can look at their distribution, and that's the sampling distribution. Okay. And so five. Now using this this sample of sample statistics, using the sample of sample statistics gets confusing, right? A statistic is a measurement from the sample. So what can I do to simplify this phrase? Usually I'll say sample statistics just to emphasize that it's from the sample, but a statistic is from the sample, right? And so here, what I can do is I can just say, recall a statistic is from a sample. So in this case, because it got so wordy, using the sample of sample statistics, I'm just going to shorthand that to using the sample of statistics, right? For example, the sample of means, the sample of R means Okay, terminology can get so boggy here, right? And so it's really important that you've got a good handle on, okay, a statistic means that it comes from a sample, making sample statistic redundant, but I use it to emphasize, right? And same thing with a parameter, a population parameter. Well, a parameter is from the population, right? But they're measurements from the population, right? So using the sample of statistics, the sample of R means, we can look at the distribution, which is the sampling distribution, right? The distribution is the shape. We can calculate the standard deviation, which is the standard error of that thing, right? And so we can calculate the standard deviation which is going to be, right, which becomes the standard error of the estimate. Standard error of the estimate. Right, it's the variability of the estimate. Okay, so the variability of that sample statistic. We can also take this one step further and we can say, okay, well, confidence intervals, right? If I have a mean, right, I can find the mean of those means, and that's how I used it before, right? We said, okay, if I know the population mean, then the mean of the means will be the population mean, right? And so now if I calculate the mean of the means, the mean of the sampling distribution, right, which I can do, then I know the center. Okay, and so now I can use this sampling distribution and I can find things like the confidence interval for the mean or whatever statistic you're talking about, right? And so we usually do not report a single statistic, right? That makes no sense. You wouldn't report just the sample mean and expect people to understand what was going on there. We need to report the variability in some way, right? And so how we do that, how we've established we do that is through a confidence interval. So we usually do not report a single statistic on its own, right? We need to also report the variability on its own. We need to also report the variability. Okay. And how we do that is through a confidence intervals. A confidence interval, combining single and plural. We do this by using confidence intervals. Right? Traditionally, we would rely on knowing the distribution of the mean in order to find the confidence interval. And so traditionally, we rely on knowing the sampling distribution, knowing / approximating the sampling distribution, which is not the case anymore, right? Not necessarily the case. So traditionally, we rely on knowing approximately the sampling distribution. And using formulas such as x bar plus minus t star, t with n minus 1 degrees of freedom times s over root n, right? But that assumes that we know how x bar is distributed, and it just kind of doesn't work for many other estimates, right? And so this is what we traditionally have been doing, and we do the same thing, but we can recreate this sort of using the Bootstrap method. And so using the Bootstrap, and I know I'm down to the wire here, but I'm almost done. So using the Bootstrap, we can find confidence intervals, and I'll just do CI, confidence intervals for any estimate or statistic. Okay. So what would we do if we have, so picking up at step 5, where I have this distribution of means or statistics, right? So picking up at step 5 from above, okay. What we would do is we would say, okay, for a 95% confidence interval, I'm going to trim off 25 or 2.5% on either end and figure out what those values are, and that's my confidence interval. Okay, so and I know I'm out of time, so if you have to go, that's totally fine. I just want to write this final part out before I let you go. So, but like I said, if you have to go, it's fine. So picking up at step 5 from above, right? We can calculate an X% confidence interval by trimming 100 minus X divided by 2% from either side, right? So 95% confidence interval, how did I know it was going to be 2.5? Well, 100 minus 95 is 5 divided by 2, because I need to subtract it evenly from both sides, right? 2.5. And so by trimming that of the R results from either end of the distribution. Okay. The trim points are the endpoints of an X% Bootstrap confidence interval. Awesome. The 2.5, it depends on if you want. So for a 95% confidence interval, it'd be 2.5. For a 90% confidence interval, it would be what? 100 minus 90 is 10 divided by 2. So then it would be 5. So it depends on what level you want. So that's why I've got this X%. Awesome. Okay. Sorry to hold you. If you have any questions, let me know, but I'm going to stop this recording, and I hope that you have a great weekend.